bird's eye overview.
This meeting is being recorded.
So today I tried to give you a bird's eye overview of some of the research we conducted during my PhD. So at ENS and Meta AI, most of which has revolved around using artificial neural networks to analyze and simulate language acquisition in children. All right, so I'm going to start with a very simple question, which is, what is language acquisition? So from a high-level viewpoint, it can be described as the mechanisms by which infants map their language environment, so their input, so what they hear, see, touch, or smell, to their learning outcomes, so including speech production and comprehension. So we'll encounter these three components later in the presentation, but for now, I want us to focus on the input or language environment. Oh, and by the way, feel free to interrupt me if like something is not clear, if you have questions or yeah, whatever. So we'll focus on the input and ask the question, how can one collect children's language environment? So actually, researchers came up with many solutions to collect children's language environment. So for instance, Deborah, a researcher at MIT, installed over a dozen cameras and microphones in his house to collect literally everything from the birth of his child until they turn age 3. So some other researchers use head-mounted cameras that allows you to collect audio and video directly from the child's viewpoint. But the solution I focused on during my PhD are child-centered long-form recordings. So briefly, some researchers in the US from the LINA Foundation, LINA stands for Language Environment Analysis, designed a small and lightweight microphone in purple there. And the idea is to equip the child with a custom-made vest with a front chest pocket in which one can insert the recorder. And yeah, the recorder can collect audio for up to 16 hours. And yeah, so maybe an important point is that the technology has been developed in the early 2000s. And it is now being used by many laboratories across the world. And yeah, and this is precisely the technology we use in my PhD to answer scientific questions about language acquisition. So for you to know a bit more about the kind of sound that is collected by these recorders, I've prepared a few audio samples that have been collected in different families and that I've merged together. So I'm not sure you're going to be able to hear the audio sample.
Pete wanders along the river. He sees T-Rex. T-Rex plays guitar. T-Rex is awesome.
I watched a video on this. I was thinking you take a leg of a peg and
he just I think he's
take those straight. That's fine.
Because it would give you total privacy there. Well, and because there's so much space. Because you gotta change it up a little bit.
The dirty dinosaur.
All right. So long forms have many advantages when studying language acquisition. So in particular, they capture our everyday language uses. And they sample the full range of the child's language environment and their linguistic production. So basically, with these two advantages combined, they allow for a big data approach to the study of language acquisition. So the idea is to collect many children over many days and to analyze this data. And if we can extract the right information from the long-form recordings, so audio that lasts for up to 16 hours, times many children, times many days, so it's a big amount of data. So if we can extract the right information from this data, we can answer many different questions. So for instance, we can study the child's language development, drawing their phonetic or lexical inventory as they age. we can study the quantity of input received by children. Maybe being given some vocalization, we can detect language disorders. Or, for instance, we may be able to measure the efficiency of speech interventions. So, for instance, how does an intervention impact the quantity of vocalizations produced by the child? So that being said, long forms are uniquely challenging. So as you've noticed in the audio sample I played, they contain a wide array of environmental noises. So you have TV, vacuum cleaner, traffic noises, cooking noises, all kind of noise. They contain close field as well as far field speech. So when someone is far from the microphone, they can contain overlapping speech when two speakers are speaking at the same time, two speakers or more. And besides, people may sing, shout, mumble, or whisper while speaking. This is naturalistic speech, everyday language uses. And another challenge is that they require costly and time-consuming annotation. So in a way, they cannot be used as is. We need first to process them to extract relevant information. So basically, if you want to annotate the whole recording, it isn't feasible. It would be too time consuming. And this brings me to the first aspect of this talk, which is the use of artificial neural networks to analyze language acquisition in children. So using the recordings I introduced. All right, so in this first part, we're going to set ourselves the following goal, which will be to build automatic speech processing tools to analyze child-centered long-form recordings. So we're going to start with speech recognition, so the task of transcribing what is being said. And a quite popular ASR system is the Watson system from IBM. So on their website, we can read Watson enables fast and accurate speech transcription in multiple languages for a variety of use cases. So it sounds very promising. So we can try it on long forms. I have an example here.
Oh, pee-pee cry time. Yeah, yeah, yeah. Yeah, we gotta sit out pee-pee cry.
Sorry, Marvin, can I stop you for a second?
Sure.
I think the people on Zoom are saying that they can't see the screen well, so maybe we can just do this.
The screen? I mean,
I don't know.
the screen is shared on my computer.
They're saying they can't just.
One time more.
Now, whatever you do there.
All right. So as you noticed, the system is not even remotely accurate. It's like of no use for long forms. So we tried a newer system, the Whisper ASR model, which has been released by OpenAI a year ago now. So it is trained on around 700,000 hours of audio. It is trained to both transcribe and translate the audio via a transformer-based architecture. So here I have an example that they give on their website. So maybe I'm going to play the beginning of the audio. So on the left you have the automatic transcript written by Whisper. I'm going to play the audio.
This is Micro Machine, representing the most miniature motorcade of Micro Machine. Each one has dramatic details, perfect trim, precision paint job, plus incredible Micro Machine pocket play sets. There's a police station, fire station, restaurant, service station, and more. Perfect pocket portables to take any place. And there are many miniature play sets to play with, and each one comes with its own special edition Micro.
All right. So basically, like the Whisper, the system like returns a perfect transcription, even though like the speaker speaks super fast. So those kind of examples are super impressive. So again, like the system seems quite promising. We can try it on long form. So on the left, you have the automatic transcript written by Whisper, and on the right, an audio sample I extracted from my long form.
He kept walking along and singing his jump, jump. He kept walking along and singing his song. I love my wet shoes. I love my wet shoes. The moral of Pete's story is no matter what you step in, keep walking along and singing your song because it's all good. The end. He kept walking along and.
So here the system seems to do like to transcribe the audio almost perfectly, but I mean this is to be taken with a grain of salt at this. I mean this is only one audio example. So to be fair, here I have an example of failure case. So on the left you have the human transcript of 2 minute long audio session. So basically there's very little speech. XXX means that the speech is unintelligible. And on the right you have the transcript written by Whisper, which makes up a whole story that has never been said in the audio. Which is quite surprising. So basically we explain this behavior by the language model component. So the model embeds a language model component. Which may make the system hallucinate speech when there's none. So basically, he created a whole story that has never been said in the audio. Something I saw quite often in the automatic transcript was so I was at the end of the audio, like there was no speech, and the system returned something like. Thanks for watching. Please hit the like button and subscribe.
But this is a lot of text compared to the fact.
Yeah. This is a lot of text, of garbage text.
Do you get it that it's thinking it's a dialect of Norwegian?
A dialect to what?
Norwegian. That's it's in there's some northern Norwegian dialect that's in the Libra voice text, like someone read a story in it once or something, and if it's background noise, I always get that label.
Oh. Yeah, completely. So basically, like on the paper, like they didn't want to say anything about like the training set they used to train the model, but when you observe those kind of mistakes, like there's no doubt that they trained it on YouTube with very noisy human transcripts. Yeah, but like more than the noise contained in the labels, I think like the fact that they transcribe the audio plus they do a language model task. My intuition is that if the model cannot rely on the audio because like background noise or whatever, then the language model component will take over and the system will hallucinate speech when there's none.
It could be partly a consequence that they're trying to be too flexible about the sound level of the inputs.
Yeah.
So if they're training it on some examples that were very, very faint, it might be barely above noise levels. So,
yeah.
So it's trying to identify with something that's experienced in its past that had that similar level of background.
Yeah, probably. So we did a more systematic analysis where we computed the water rate obtained by Whisper on 2 minute long audio sessions collected in American English speaking families. And the water rate is not that good. So on average, the system obtains a water rate of around like 50%. So on adult speech, female adult speech and male adult speech, the system obtains around 40% water rate, whereas on child speech and electronic speech, we are at 100% word error rate. So, so the lesson of this short study is that so basically even today's most performance systems are of no use on long forms. We cannot use like off-the-shelf tools. We need to find some strategies to make them better. And I think in the case of ASR, like there exist strategies that may improve their performance on long forms. Like we haven't tried fine-tuning them on long forms or those kind of things. There's clearly a domain mismatch between the training set used to train the system and our data sets. So that was it about speech recognition. So I'm going to go back to the Lina Foundation, which designed the recorder. So they also came up with a speech processing pipeline to automatically extract information from these day-long recordings. So the first step of their algorithm involves segmenting the audio into broad speaker categories. So female adult speech, key child for the child wearing the recording device, other children for any other child in the environment, and male adult speech. So from this segmentation, they derive what they call conversational turn count, which is the number of turn counts between an adult speaker and the key child. Then there is a third step that estimates the number of words produced by adult speaker, AWC for adult word count. And then a last step that counts the number of vocalizations, speech-like vocalizations produced by the child, so filtering out cries, laughs, and so on. So as I said at the beginning of the presentation, the Lina recorder and speech processing pipeline is currently being used in many laboratories across the world. So yeah, it has had like a huge impact on how people study language acquisition, basically. So during my PhD, we identified and others 3 limitations of the Lina solution. So first, it is closed source, which makes it hard to access implementation details. So it is used as a black box, basically. Plus, the speech processing pipeline is only usable with the Lina recorded audio. So if you use your own USB microphone, for instance, you cannot use the Lina algorithm. The second limitation is that the technology they use to develop the speech processing pipeline is aging. Like it has been developed in the early 2000s, so a time where GMM, HMM were the state of the art. So the idea is that with 2 decades of progress in speech technology, we may expect better performance. And the third limitation is that it has been only optimized for American English, which may hurt its performance on other languages. So the challenge we took was to build a free and open source alternative to the Lina speech processing pipeline. So first, we developed an alternative to the segmentation algorithm, which we called the voice type classifier. So identifying which voice type is activated in the audio. So briefly, like the model we chose, although it's not that important. Like we have a SyncNet network that learns filter features from the raw speech, followed by a stack of LSTM layers and a stack of feed-forward layers, and the model returns the probability for each of the 4 classes we're interested in. And it is trained using the binary cross entropy that is commonly used for classification problems. So to train our model, we gathered 260 hours of child-centered long-form recordings that have been annotated for the task we're interested in across 10 different languages. And we were quite happy with the results we got. So we obtained a quite strong improvement on the key child class and the female adult class. So 13% and 20%, and we obtained more minor improvements on the other child and the male adult classes. So the idea is that using our model, researchers can have a more accurate view of the quantity of input received by the child, as well as the quantity of vocalizations they produce. And our model is available on Git. So you'll find the code and a pre-trained model if you want to try it. So the second challenge we took was to replace the AWC estimate of Lina, so the adult word count. And to do that, so we use the voice type classifier I just introduced. We extract various features. So we consider both signal level features and pre-trained features, so playing with pre-trained models. And then the model is quite simple. Like we have linear layers that maps the features to the number of words produced by adult speakers, the number of syllables, and the number of phonemes. So I won't go over the details of the evaluation, but here you have the correlation coefficient between the estimates, the numbers estimated by the system and the numbers returned by the human annotator. So the purple bar, which shows the score obtained by Lina, is to be compared with the yellow bar, which shows the score obtained by our system for the word count estimate task. And so basically what we see is that in most cases, our model is either on par with the performance of Lina or better than Lina. The only exception is the MCD corpus, for which Lina is better. And this is also the corpus for which the two algorithms seem to struggle the most. So yeah. So again, so this work has been led by Okorasan and in Finland. So again, we released the model on Git. So if you want to try it, you can download the pre-trained model and run it on your data. So going back to our goal, which was to build an alternative to the Lina speech processing pipeline. So we built a voice type classifier from which the CTC measure is derived. We built an algorithm that estimates the number of words produced by adult speakers. I haven't worked personally on the child vocalization count, but I know that there's ongoing research on this problem. So hopefully one day we will also have a solution for this problem. So in comparison with Lina, our pipeline is free and open source. It relies on state-of-the-art technology. It has been trained on multiple languages and evaluated on multiple languages as well. We showed that in most cases it performs better than Lina. All right, so some key takeaways from this first part. So as we've seen, off-the-shelf tools do not work on long forms, which means that we have to build our own tools dedicated to processing child-centered audio. And I hope that by now you are convinced that child-centered recordings offer speech experts an amazing playground, and actually the community of speech experts interested by long forms is growing. So some recent papers. So we have. So for instance, Björn Schuller's team has looked at classifying infant vocalization maturity. You have some paper from McElwain as well. Narayanan's team working with children with ASD, and Marshman's team on classifying infant-directed speech. And as the community is growing, I think it's important that we make sure we stick to good practices together. So this includes model and code sharing, preferentially an easy-to-use model. This includes writing a comprehensive documentation and evaluating our models against peers as well. Just that we get to know like which model performs better in which settings. So to conclude, so one goal of language acquisition might be to study language acquisition in the 7,000 languages that are being learned worldwide by children. And Personally, I think that the only way we can do that is to use algorithms. We cannot possibly collect and annotate data for the 7,000 languages. And I think we need algorithms to scale on our analysis to many different settings, to many different languages. Although like algorithms won't replace manual annotation, but they can really accelerate our analysis. And yeah, that's it. So so as we will see later in the presentation, long forms can be used to study children's language environment, but they can also be used to fuel computational models of language acquisition, so to run simulation of language acquisition, which is the second aspect of the work I did during my PhD. So using artificial neural networks to simulate language acquisition in children. All right, so before we dig in, we can have a look at some of the developmental milestones during the acquisition of sounds and the acquisition of words in infants. So regarding the acquisition of sounds, we know that at 6 months, infants discriminate native sounds as well as non-native sounds. And it is only 6 months later that we observe an increase in infants' capacity to discriminate native sounds and a decrease in their capacity to discriminate non-native sounds. So in this short time span, they become language-specific listeners. So regarding the acquisition of words, we know that on average, infants start to recognize their own name at 4 months. At 6, they recognize the auditory form of frequent words. And for their first birthday, an infant typically comprehends around 80 words. So what this timeline shows is that infants learn about the sounds and the words of their native language in a parallel fashion. They learn about the sounds and the words at the same time. It's not one after the other. And this was one of the goals we tackled during my PhD. So it was run a simulation reproducing this gradual and parallel learning trajectory. So briefly, the idea is to build an algorithm that reproduces some behaviors observed in infants. And by doing so, we can get precious insights about the kind of cues infants may rely on to acquire like a given knowledge to learn their native language. So here's the approach. So we have a model of the environment. So the input the child receives. We have a model of the learner. So the mechanisms responsible for learning, and we have a model of the learning outcome. So how we evaluate the model's language capabilities. So for this first study, we used English and French audiobooks. So this is our model of the environment, and the idea is to simulate the development of an English learning or a French learning infant. For the learner, so we use a self-supervised algorithm that works from the raw speech. So briefly, it is made of an acoustic model. So it's like a contrastive predictive coding model plus k-means. So the acoustic model is trying to predict the near future and maps the continuous speech to a discrete representation of it. And from this discrete representation, we train a language model that is trying to predict the next unit. So I don't think it's like super important to understand like all of the components, but the key idea behind the learner is to learn by predicting the near future in the audio stream, being given the past context. So for this study, we consider 2 evaluation tasks that are directly inspired by how we evaluate human language capabilities in the lab. So we have a sound discrimination task and an evaluation task at the lexical level, a spot the word task. But I'll give more details about the evaluation now. So first, about the sound discrimination task, we used an ABX paradigm. So in this task, the machine is being given 3 spoken triphones. So for instance, lip, lop, and lip. We compute the representations of these triphones, and the machine succeeds if the distance between the two occurrences of the same tryphon is lower than the distance between the two occurrences of the different tryphons. So lip and lip closer to one another than lip and lop. And finally, we ran this procedure on millions of tryphons over all possible contrasts in either English or French. So about the spot the word task. So in this task, the machine is being given a word, a real, let's say, English word, and a pseudo word that sounds like a word that has been matched in phonotactic probability. So for instance, cookie, a real word, a real English word, and kuni, which is not a word in English. So we compute the probability of each of the stimuli, and the machine succeeds if the probability associated to the real word is higher than the probability associated to the pseudo word. And again, we run this procedure on thousands of pairs in both in either English or French. All right, so following the methodology used in psycholinguistics, we follow cross-linguistic design in which we train a model either on English or French, and we evaluate them on their native language, so English on English, French on French. This is our native condition. But we also evaluate them across languages, so the English model on French and vice versa, and this is our non-native condition. So the idea is to be able to measure what our model has learned due to exposure to its native language as compared to exposure to another language. But I think it's going to be a bit clearer with the results. So here you have the results on the sound discrimination task. So you have the phonetic score computed on the ABX task for models trained on varying quantity of speech in both the native and the non-native condition. So what we observe is that with more exposure to speech, models become better at discriminating sounds, and this is true in both the native and the non-native conditions. So being exposed to English helps you better discriminate French sounds as well, and vice versa, which makes sense given the high number of common sounds across these two languages, and because we are looking at like quite low-level language capabilities. Another interesting observation is that the gap between the native and the non-native model tends to increase with the quantity of speech. So in a way, models become more language specific with the quantity of speech. So the English model becomes progressively better than the French model at discriminating English sounds and vice versa. All right, and I think that's it about this graph. So for the spot the word task here, things are a bit different. So so we observe a performance improvement only in the native condition. The model becomes better at spotting the word with the quantity of speech. But here in the non-native condition, the line is almost flat. There's not as much learning as in the native condition, which makes sense, again, like being exposed. Yeah.
So the quantity of speech in that second one, is that in training or in testing?
This is a testing type.
Okay.
Yeah. Yeah. So again, like the relatively flat dashed line makes sense. Like receiving English utterances doesn't help you to know like what a French word sounds like. Yeah. So in a nutshell, we observe a gradual and parallel learning across the sounds and the words, which was our goal at the beginning of the study. A bit similarly to what we observe in infants, our model learns about the sounds and about the words at the same time. All right, so to conclude on this first modeling study, we have a model that learns to discriminate sound. It learns to identify word forms. It does so better than a non-native model in a gradual and parallel fashion and without any supervision. Our model only receives the speech stream. So the question we're interested in is what do these results mean for infant language acquisition? So first here we have a demonstration that the necessary signal is present in the speech stream to instantiate knowledge at the sound level and the word level. And second, we show that this signal can be extracted using a statistical learning mechanism, which does not mean that infants employ similar strategies to learn about the sounds and the words of their native language, but this shows that they could rely on similar cues to start learning about these two aspects of their native language. Do you have any questions so far? All right. So the results are presented here, and many more analyses have been submitted to developmental science, and the paper is currently being reviewed. All right, so modeling language is a really complex task, and to overcome this complexity, researchers have used simplifying assumptions regarding the input. So for instance, models of early phonetic learning use data points sampled from Gaussian distributions of words spoken in isolation. And models of early word learning have used artificial languages or strings of phonemes. But as we showed with this audiobook study, and I mean, this has been shown by many other researchers, nowadays computational models can learn directly from large quantities of speech, clean speech at least, and they can learn language as a whole. We don't have like only a model of early phonetic learning or early word learning. We have models that learn language as a whole. But still, infants do not learn from large quantities of clean speech. And here I argue that the cues the algorithm learns from might be very different than the cues infants learn from. Basically, if you train an algorithm on audiobooks, you cannot make sure that it's going to learn from cues similar to the cues infants learn from. Kind of like the rationale is that by oversimplifying the input, we may end up studying a completely different problem than the one infants face. So this will be, this was the last goal of my PhD, to run a language acquisition simulation from what children truly hear, so using child-centered long-form recordings. So actually, there are reasons to be concerned about how the differences between audiobooks and long forms may impact the learning problem we are trying to solve. So first, language uses in long forms are very different than language uses in audiobooks. So we found, for instance, a much lower proportion of speech in long forms than in audiobooks. In our data, we also found a higher proportion of female speakers in our long forms, whereas it's a bit more balanced in audiobooks. And we also have a much shorter time duration in long forms than in audiobooks. In audiobooks, like basically one speaker reads the whole chapter, so you're going to have long stretches of speech read by the same speaker. So we can ask the same question about the recording conditions. So actually, we knew just by listening to the audio that long forms were quite noisy, but we didn't have a way to measure that quantity of noise. So we had to build a model that extracts the speech to noise ratio and the C50 measure that I'm going to present a bit later on. From the recording. So we have maybe like for those who don't know, the speech to noise ratio measures the level of speech with respect to the level of background noise. So comparing audiobooks with long forms, we observe that long forms have a much lower speech to noise ratio, indicating a higher level of background noise. So I've prepared audio samples at both ends of the distribution. So low SNR utterance.
So that Dino's, that Taylor place, you know, like, I don't know if I told you about it or not, but Jeff Cameron, I'm like, Jeff, where should I go to get tailored, you know, to get the suit tailored for the wedding? He goes, oh, just go to Dino's. I'm like, oh, that's convenient, I know.
I mean, maybe you don't hear clearly, but it seems like we're in the car, like it's yeah, it doesn't seem that clean, like there are a lot of background noise. So an example of high SNR U-turns.
Because I told her I would come down to help out, you know, and she said no.
Oops.
Because I told her I would come down to help out, you know, and she said no.
Yeah, so here the speech signal is a bit cleaner. It stands out more than the background noise. So we did the same with the C50 measure, which is a measure of reverberation. So again, we compare audiobooks with long forms. We see that audiobooks have quite good reverberant conditions, very little reverberation, higher is better. Whereas in long forms, you have a whole range of reverberant conditions with environments that do not reverberate speech a lot, and others that for which we find strong reverberant conditions. So similarly, I prepared audio samples. So low C50 U-turns.
So I know that you guys will all be relieved less inspired by what she has to say.
So here, like, the speech is distorted in a way that is very typical of reverberation. An example of high SNR U-turns.
And then I looked up the tickets for it, and they were like ridiculous.
So here it's better. Like the speaker seems quite close to the microphone, and we can clearly hear what is being said. Anyway, so all of that to say that language uses in audiobooks and long forms are very different, and recording conditions in audiobooks and in long forms are very different. And there are 1,000 ways in which these differences may impact the learning problem. So yeah, the model that predicts the speech-to-noise ratio and the C50 measures has been published in Interspeech, and again, you can find it on Kit if you're interested in measuring the quantity of background noise or the quantity of reverb in your audio files. So in light of the difficult learning conditions we found in long forms, we had to come up with a new strategy to build our learning model. So on the left, you have the base learner, the same as the one I presented in our audiobook study. So acoustic model, language model, and so on. It's the exact same model. And on the right, you have the same learner, but that is augmented with what we call inductive biases. And by that, I mean mechanisms that have been designed to guide the learning process, to help the learner learn relevant information. So we designed 3 inductive biases. The first one is voice activity detection. So the model embeds a voice activity detection module that is pre-trained and that forces the model to learn only from the speech segment, to discard the non-speech part of the signal. The second inductive bias is a speaker separation mechanism that forces the model to learn speaker invariant representations. And we have a third inductive bias, which is simply data augmentation, and that forces the model to learn pitch and room invariant representations. So we argue that these 3 inductive biases are plausible given what we know of infants. So for instance, we know that newborns come with a preference for speech over non-speech, which shows that they can discriminate speech from non-speech. They also show early abilities to discriminate human voices, and their perception shows some degree of robustness with respect to a change in pitch. So I haven't found any study that shows the same for reverberation, but this is something we could try. Yeah. So here you have the result of the base learner in blue trained on audiobooks. On 128 hours of audiobooks. So we observe that the model gets okay phonetic accuracy. And so we have the second measure is the native advantage. It's just the gap between the native and the non-native condition. So it measures the extent to which the model develops a language-specific perceptual space or representational space. So in that specific case, the model seems to develop a language-specific perceptual space, a bit like what we observe in infants between 6 and 12 months. Yeah, this is what I said. So here we have the same learner trained on long forms. So we observe a loss in phonetic accuracy, and here the model doesn't develop a language-specific perceptual space. So in other words, the English model, the model trained on English data, will discriminate English or French sounds as well as the French model.
Does the long form training exclude the child's own utterances?
Yeah, actually we tried with the child's own utterances, and it didn't make any difference in terms of phonetic accuracy. But that's a good question. I feel like you could really do both. Like, I mean, I feel like some psycholinguists may be angry with the choice we made, you know, like because they would consider that the child's own outputs is part of their input as well, which makes sense. But yeah, for that study, we decided to discard them.
Yeah, I mean, I just think it's obviously more about learning to speak, you know, the child's own voice, because when you're speaking at the same time, you know, things change, their middle ear contractions, it's really,
Yeah.
you know, situation. So.
Yeah. Yeah. So this time we train the learner with inductive biases, so voice activity detection, speaker separation, and data augmentation. So the loss in terms of phonetic accuracy we observed earlier vanishes. The model recovers from the loss we observed earlier, and it starts to develop a language-specific perceptual space again. Although, like, we don't go up to the native advantage we obtained when training on audiobooks. Yeah. So in a nutshell, yeah.
Sorry, can I just say, on one of your biases is that the model, go back to the bias.
Yeah, sure.
So I don't get it wrong. So the model, like, is forced to separate the speakers.
Yeah.
And it does that through training, like, you're not just.
It's those are pre-trained capacities in a way. We could have done it in an unsupervised fashion, although, like, no one does that. I feel like, I mean, but that would be super interesting. Even the voice activity detection, we could have find strategies for the model to discover what is speech in non-speech during training. But actually, we don't know if that's possible, you know, to learn this kind of information while learning to discriminate sounds, while learning to identify word forms. And I think this is an open question. But the day I have a model that learns to do all of that plus discriminate sounds, like, I'm going to try it on long forms.
I was just wondering if there's, like, some work that's been done by someone who works in the department, showing that actually people are really bad at telling voices apart.
Yeah.
So I'm just thinking of how that fits with the assumption that the model will definitely be able to tell voices apart.
Well,
it might just be completely different situations.
Yeah.
Connecting these two bits of research, maybe just not connected, but.
So what results show that models are bad at discriminating voices?
People, if you give people a whole set of, like, tokens from 2 different speakers, they quite often say there are 8 different speakers, for example. People are just not very good. Like, if you give them clips from movies, for example, at working out which speaker is saying what. Yeah. So I feel like that assumption is maybe not valid, but I don't know if that's fair, because it might just be these things might just not be saying.
No. I think, I mean, this is an interesting feedback. So first, I want to say that this module as well, those are not perfect models. They do mistakes, a lot of mistakes actually, because we don't have the labels in our long forms. So those are pre-trained models. We train on long forms with our labels. They do a lot of mistakes. So in that sense, I feel like this is actually similar to what humans do. I agree with you that I mean, this is, you could use a perfect speaker separation mechanism. I would tend to say that this is a bit oversimplifying the problem, because I don't think children are capable of perfectly separating speakers neither.
I guess in your data, there are always conversations that are happening with somebody in
Yeah.
person, right? So
Yeah.
obviously the child's got a million other
Yeah.
the voice is
Yeah.
coming from, so maybe a bit more sensible to make that assumption. Then they're not just listening to each other, they're in the context of
Yeah.
the interaction.
Yeah.
It's kind of different.
Definitely.
Yeah, they're looking,
Yeah, of course, they're in an environment where they can see
they're
the
seeing the first thing, not to mention all the phonetic information.
Yeah.
Yeah, it's
Yeah.
a bit different.
You're spoiling my conclusion.
I'm trying to speak up.
Yeah, so in a nutshell, what we showed with this study is that considering inductive biases in our modeling experiment may be important, at least if we want to train our model on naturalistic data, and that's. And to me, infants are not tabula rasa. They come with some mechanism that for sure help them learn about their native language. So maybe we might need to integrate that in our modeling experiments. All right. So here you have a full comparisons of models trained either on audiobooks or on long forms for varying quantity of speech, from 4 hours of speech to 1,000 hours of speech, and all models are trained with inductive biases. So on the left, you have the performance on the sound discrimination task. So we observe that models trained on long forms are a bit worse than models trained on audiobooks. But what's important is that there's learning in both conditions. Yeah. Okay. Awesome. On the right, you have the same results on the spot the word task, lexical accuracy. And here we observe learning for the model trained on audiobooks, but the model trained on long forms doesn't seem to learn anything. It is at chance level, despite the inductive biases we implemented.
Could you say, because one of the things about the long form is how many different children are we talking about, and how many?
15. Yeah, 15.
15.
50.
50.
And how many different speakers do you have on the audiobooks?
Well, it depends on the no, your question was how many speakers in the long forms?
Well, I mean, both.
How many kids or how many speakers?
I think, but how many children, which gives you some idea about how many different speakers might be involved, and it sounds like it could easily be 100.
Yeah.
Because it depends on family.
Yeah.
Yeah. Right.
Yeah.
But in,
Yeah.
If the child goes to the park or like.
right. But in the audiobooks, how many different?
In audiobooks, you have I can't remember the number, quite a high number of speakers. Although like the data you found in LibriVox and so on, like it's a power law. You have a few speakers that read a lot of audiobooks, and then it goes down. So I would say you have more speakers in audiobooks than in long forms.
Is there not more speech in audiobooks? Because in ordinary...
Not with the inductive biases, because we do voice activity detection, so both models receive only speech. This was true in this graph. Here the quantity of audio is the same, but the quantity of speech is different. Quantity of speech is approximately the same here because you have almost no non-speech signal in.
And were the two tasks controlled for noise levels and so on as well?
Oh, what do you mean by that?
Did you artificially introduce noise into the audiobooks or anything like that?
Oh yeah, I did that, but those are not results I'm going to present today. But what I did, like, kind of to better understand what may help the performance of the model, what I did is that I took audiobooks and I added additive background noise and reverb for various level of speech-to-noise ratio or C50 measure, and we observed that performance decrease as a function of the quantity of noise and reverb. In a way that's what's interesting to me. In a way that is not, you cannot recover from this loss. So basically, the learning rates. So if you do that for varying quantity of background noise, The curves never cross.
Okay, so the blue curve's always above the.
Yeah. Yeah. So basically we did that up to 1,000 hours of data. So what this means is that even by adding data, you cannot recover from a loss in.
But the audiobooks, they're probably mostly trained speakers. They're mostly actors and things like that. At least audiobooks I've come across. So they're not. They're trained to talk and speak in a particular way, whereas the long form speech, it would be just any parent or.
Yeah. When in audiobooks, those are not trained speakers. It's like volunteers recording themselves at home. Okay. But I mean, you're right. Like this is read speech. This is not spontaneous speech, which is another difference, important difference between audiobooks and long forms. Although, like, this is a direction we haven't explored. We haven't tried. I mean, it's quite hard to study the impact of read speech versus spontaneous speech on the learning outcomes of our model, but that would be really interesting. I think this is an important problem. And same, like, I don't think you can make the assumption that infants learn from read speech. Like, they do receive read speech, like during storytelling and so on, but this is a minority of the data they receive. All right, so maybe the conclusion. So what we showed is that inductive biases are important, but despite them, we have no evidence of learning at the lexical level. So in a nutshell, we showed that the learning outcomes developed by our model are exquisitely sensitive to the input signal. And I think this is important for methodological reasons. As I said, like oversimplifying the input data may lead us to oversimplify the learning problem. So our goal at the beginning was to build a language acquisition simulation from realistic data. And I think with this study, although not our results are not perfect, we showed that we have both the data and the models. So data and models are ready, so we can start thinking about this problem. But if we want to build a language acquisition simulation from naturalistic data, the problem becomes much harder than using audiobooks or strings of phonemes and so on. But I think, like personally, I think that it becomes also more rewarding as by using naturalistic data, you make sure the cues your algorithm learns from are also accessible to the child. Whereas if you use strings of phonemes, so you cannot make sure that infants rely on strings of phonemes or that they have access to, let's say, phones or whatever. And same for audiobooks. So the differences we observe between our models trained on audiobooks or our models trained on long forms raises the question, what do children have that our models don't? And as you mentioned, so first, infants probably have many more inductive biases that we haven't implemented yet. Some of them that have been documented by psycholinguistic studies, but I'm sure that children come with many more inductive biases that we are not aware of. For instance, like infant speech perception is rarely studied under adverse conditions. Like if you vary the speech to noise ratio, what does happen? Like do infants still discriminate sounds or do they fail? This specific experiment, I think it has been done, but it hasn't been done in the case of reverb, let's say. So I feel like we still know very little about how the child's perception is impacted by adverse conditions and how this changes as a function of the child's age.
And the other thing I think that's important to remember is you've got a single microphone. Right?
Yeah.
And children have two ears, not one, and that makes and a head in between.
Most children have 2 ears, but not all of them.
No, but most of them.
most of them, and I think this is typically the kind of inductive bias we might think about, like if we integrate like a source separation algorithm, like what happens.
Well, I think it's more to do with the fact that because you're getting independent signals and you can get spatial separations, and then it's much easier to pick out
Yeah.
different talkers.
Yeah.
I mean, it has an enormous impact.
Yeah, definitely.
In theory, on,
Yeah.
on the sort of organizing the auditory
Yeah.
scene.
Yeah.
And there's really, I guess there's really nothing like that in these models.
No,
Directly.
no, definitely. Yeah. Mm. But it's an interesting feedback because this means that we need to step back and think, oh, okay, do we want to use a single channel microphone, or do we need to design a new microphone? And I think, yeah, I mean, it's related to the question, like to which extent can we reconstruct the child's language, the child's sensory inputs, actually. By recording only audio, we take only a subset of these inputs. Single channel, still, I mean, again, a subset. So yeah.
And you're not getting the visual stimuli.
Yeah,
Exactly, which is my second point. So yeah, yeah. Obviously, like children have also access to other cues, visual or social cues that may be. Not all children. Thank you. Exactly.
And then we're chatting with a parent and carer, it could be
Yeah.
tactile.
But again, like, what do we know about the perception of really young children suffering from hearing losses, for instance? Much less than for typically developing children, unfortunately. But that would be. I mean, this is really like important information if you want to model language acquisition. Yeah. So yeah, those cues may help infants achieve better and faster learning. So yeah, those results have been published in two publications, one under review in cognition and the other one which proposes a benchmark to evaluate models trained on naturalistic data that has been published in Interspeech. I think it's not necessary, but basically, yeah, briefly, like this is kind of the ecosystem we've been trying to build with my supervisors. So we have language researchers that collect data, like Hannah. So as speech experts, we can build supervised annotation tools for them to use and to analyze their data. And this same data can be used to build computational models of language acquisition. And actually, so this is not something I emphasize in the talk, but the tools I built like allowed me to run more modeling experiments. So for instance, with my tool estimating the SNR, I could filter out noisy utterances and see if it has an impact on the learning outcomes developed by my model. Same for the voice activity detection mechanism and so on. So yeah. This achieves to show our artificial neural networks can be used as a tool to analyze language acquisition and as a model of the infant. And yeah.
Okay. Thank you so much. So we are over time, so if anybody needs to leave, please feel free to do so. But we will take some questions and then we have a reception afterwards with Marvin. So do any of the students or postdocs have questions before we take questions from anybody else? And that's also open for people on the chat. I don't know if you can see the chat. Any questions? Anybody? There are questions here.
No, it was at the beginning of the talk.
Okay. Okay, questions from anybody else?
This is going back a very long time when I was doing my own PhD, which is 20 or more years ago. But I did see, I don't know if it was taken any further, but I did see a study which I think was from MIT, where they tried to incorporate the visual stimuli by having a sort of robot with a camera, and they mimicked a parent interacting with a child. So they were saying things like red ball and holding up a red ball. And I can't remember, it's a long time ago.
Yeah.
I can't remember how far they took that study and
Yeah.
really followed it up.
Yeah, there are many interesting studies. So exploring more like the impact of the social or visual cues in language learning. One thing I realized during my PhD is that if you go that direction, like then you're doomed like to use more toy-ish data, less naturalistic data. Usually like people studying the impact of visual cues, they're going to use like, let's say, image caption pairs. That's fine, but
So
I mean,
I think this was actually using maybe transcripts from actual parent-child
Okay.
interactions and then reenacting them. So
yeah.
imagine when parents said red ball and held up a red ball, they then do that in front of the robot camera and so on.
I don't think that's easy because like if the child doesn't look at the red board, then the information is lost from the child's viewpoint, but not from the robot's viewpoint. But I think this is like an interesting approach. The approach we took was more like, okay, we want to go full naturalistic. We're gonna put microphones on children and we're gonna
Edge handles or something.
Yeah, head-mounted cameras. We could have used them, but you lose in you cannot sample the full range of the child's linguistic experience because they cannot wear head-mounted cameras for a whole day. It's too heavy. But in 5 years, maybe we'll have better hardware, and we're gonna be. I mean, this is gonna open new modeling opportunities.
I don't know if you're actually able to answer this, but was it taken into account any kind of internal language that was being used? Because, I mean, from the research, we don't particularly know what happens in sort of very young children's kind of brains as they're learning languages. Are they using language internally?
Yeah.
Kind of relates to, whether or not they're utilizing their own speech.
Yeah.
And I guess it would depend on whether or not they were utilizing their own internal speeches, like covert speeches.
Yeah.
But I guess if presumably the model is not self-producing any speech.
Yeah, it's a perception model, not a production model. But I guess you could explore that question with self-producing models. Although for very young children, like I don't think those kind of mechanisms, if they exist, are too important. I mean, at 6 months, like you do understand some words, but I mean, your language knowledge is very, very limited. Yeah, but that's an interesting question.
Sorry. I think in your first study that you described, there for both of the systems in Lena and your model, they did relatively poor on 2 of the classes. So it was like the older children class and the male adults.
Yeah.
So was that reflecting some advanced compensations of the sample?
Yeah.
Or
Exactly.
Just because of that? Or
just because of that, yeah, probably. No, for other reasons as well. So my suspicion is that when you do hear male speech in the recording, it's usually further away from the mic than female speech, let's say. I mean, at least in our data, which have been collected in various settings, actually. So class imbalance is problematic, but the position of male speakers, the average position of male speakers with respect to the microphone might play a role. But yeah, other child and male classes are in minority in our data sets and in long forms in general.
It depends on the culture.
It depends on the culture.
Some of the data from Marissa's
exactly.
field work. She studied communities in Papua New Guinea and Mexico, and these children hear more input from other children than from adults.
Yeah.
And so it's going to be different depending on where you study and what kind of data you have.
Yeah, exactly. So there are a lot of improvements that can be done. I think using more data, for instance, we tried so many strategies to alleviate this problem of class imbalance because this is a well-known problem in the literature. None of them worked. So yeah.
Right. So I guess we can continue these conversations over wine and some snacks before Marvin has to go back to France. So let's give him a round of applause.